and welcome to this video on OCR salters, bonding and structure. This is for the Elements of Life topic. My name is Chris Harris and I'm from AlleryTutors.com, and basically this video is going to give you an overview of the topic of bonding and structure, of the subject bonding and structure for the Elements of Life topic. We got that out eventually. Okay. So yeah, basically we're just going to give you an overview. It's ideal for revision. The slides that I'm going to be using on here, they're great for revision as well. You can purchase them if you just click on the link in the description box below this video. You'll be able to hold of them there. They're great value for money, really good to supplement your revision. You have your own copy of them, etc. So and they're just done on PowerPoint, so they're pretty compatible with the vast majority of computers out there. So yeah, fill your boots. Okay, like I say, these are specifically for OCR salters, the salters course, and they match these specification points that are put on here, as you can see, and they're just taken straight from the syllabus. So if you're doing salters, you'll be alright. Okay, so let's start with ionic bonding. So ionic compounds are basically where you have oppositely charged ions, and they're attracted to each other by an electrostatic attraction. Okay, so we've got a positive and negative. So let's just look what an ion is first. You can see we've got sodium on the left. So sodium has one electron in its outer shell. Now for it to become stable, it's going to lose that electron and give it up to another atom and then be attracted to it, form a type of bond. And it's this attraction that gives it the stability. So you can see here that we've got sodium with one electron here. Chlorine, for example, has 7 electrons in its outer shell. It only needs one more to get that full 8, or the octet rule. So it gets one more electron and then they attract because they then form ions. So let's have a look. Electron moves away and you form a positive sodium ion and a negative chloride ion. And they now attract each other because they're oppositely charged. They have an electrostatic attraction. So looking at these ions then, you get plus ones for group 1s because they have one electron in the outer shell. So they lose that electron to form 1+ ions. Group 2s form 2+ ions. Group 3s form 3+ ions. Group 5s, they have 5 electrons in their outer shell, but it's easier for them to gain 3 than to lose 5. So that's exactly what they do. So group 5s, they gain 3 electrons. Group 6s gain 2 electrons, that's why they form 2-. And group 7s gain 1 electron, that's why they form 1- ions. Okay, you need to know some molecular ions as well. You need to know, for example, hydroxides are OH-. Nitrates are NO3-. Ammonium is NH4+. Sulfate is SO4 2-. And carbonate is CO3 2-. So you can see here that you need to know these specific molecular ions. Okay, so we can work out the formula of an ionic compound. We can use a swap and drop method. So you can see here what we do is you write the 2 ions. This instance we're going to use calcium 2+ and a nitrate ion, which is NO3-. We're then going to swap the charges over. You can see we've just swapped them. We're then going to drop the charges, as you can see on there. So we've got rid of the minuses and pluses as well and dropped them, so they're lower. And then we combine them and simplify if we need to. Because this is a 1:2 ratio and it's already the simplest way, then we just leave it as that. And this is calcium nitrate, CaNO3 2. The brackets mean that we need 2 lots of NO3. Okay, so we need everything inside that bracket to be multiplied by 2. Here's another example. Calcium 2+ and O2-. Swap and drop. So we swap the charges over. We drop the charges. As you can see, get rid of the pluses and minuses and put them smaller. And then we write them down and we simplify. Now, because this is Ca2O2, obviously a 2 to 2 can be simplified to 1 to 1. So calcium oxide is CaO. Okay, and then you would simplify it. Okay, so ionic compounds like sodium chloride, these have a giant ionic structure. So you can see here, you've got sodium ions which are represented by the yellow spheres, and the purple spheres are represent the chloride ions, or Cl- ion. Now they form this regular structure, okay, so you've got all these ions in neat rows, a cubic shape, and it's a giant repeating pattern, so it just keeps on repeating and repeating and repeating, okay? And this is a classic structure of sodium chloride. Now, most ionic compounds, they do dissolve in water. Molecules are polar, water molecules are polar, so they attract to these charged ions within the structure, and what they do is they pull the structure apart. So the positive hydrogens on the water molecule, the delta positive hydrogens on the water molecules are attracted to the negative ions, which are the purple ones, in sodium chloride. And the delta negative oxygen on the water molecule is attracted to the positive ions. So that's why it pulls this structure apart, so they dissolve. They do conduct electricity when they're molten or when they're dissolved in solution, because the ions are free to move around, but they won't do that if they're a solid, because the ions are not free to move around because they're in this rigid structure. And they also have high melting points. There's loads of, or many strong electrostatic forces of attraction between these oppositely charged ions. So that means you need lots of energy to overcome these forces. You've got to make sure you are, if they ask about this, that you're writing words like that, especially the ones that are underlined, because they are your key words. Okay, covalent bonding then. So covalent bonding is the sharing of outer electrons in order for atoms to obtain a full shell. Okay, so unlike ionic bonding, where we had one atom donating an electron and the other one receiving, this is where they're sharing them. So we do have this electrostatic attraction again, there's that word again, but this time it's between the shared electrons in the middle and the positive nucleus of the two atoms. So we have single, double and triple bonds, as you can see on there. Basically this is just where we've got more electrons being shared. So in a single bond we have 2 electrons being shared, in a double bond we have 4 electrons being shared in total, and in a triple bond we have 6 of them being shared. Now covalent bonds can be represented with lines as well, and you've probably seen them like this. This is an example of how a covalent bond can be represented. And dative covalent or coordinate bonds are where you've got one atom donating 2 electrons to an atom or an ion to form a bond. Now these aren't as strong as a traditional covalent bond, but they're useful for things like H+, for example, which doesn't have its own electrons, to bond with another atom, because it can't bond through a normal, a conventional covalent bond, because it doesn't have any electrons to share. So thankfully, another atom, if it has 2 electrons like this, a lone pair of electrons, it can donate both of them to the H+ and form a bond, like this. There it is. Okay, there's your dative covalent bond. Both the electrons in the nitrogen are donated to the H+ ion. Okay, and we can use an arrow to represent a coordinate bond as well. And you can see here that this arrow is obviously showing the direction of the electrons being donated. So it's gone from the nitrogen to the hydrogen. And obviously the whole thing is a plus charge, and it's an ammonium ion. Carbon monoxide has a double covalent bond, and it has a coordinate bond as well. And you can see here, obviously there's the structure that's been drawn. You can see that we've got 2 crosses and 2 circles showing the standard double covalent bond, and then we have 2 electrons here coming from this oxygen, and that's the coordinate bond. So this oxygen is giving up electrons to the carbon, so that's a coordinate bond. Okay, giant covalent structures. So examples of giant covalent structures include graphite and diamonds. So graphite, each is basically layered, as you can see in the diagram. Each carbon is bonded 3 times, with the 4th electron being delocalized. You can see it's been delocalized here. Okay, so but if you look at each carbon atom here, it's bonded 3 times. So there's one there, so it's one bonded, one there, and one there. So it's bonded 3 times, with the 4th one being delocalized. You can see by that dotted line. So there's lots of strong covalent bonds. It means it's got a really high melting point, and graphite does. It's really difficult to melt because there are many strong covalent bonds. We have layers as well, like we said. That's one of the first observations we could make. They slide over each other easily because we've got these weak forces between the layers. Makes them ideal for use as pencils for that reason. And we have delocalized electrons between the layers. This allows graphite to conduct electricity, so it carries a charge through the graphite structure. And the layers are actually quite far apart in comparison to covalent bond length. So that means graphite is actually quite low density, which is useful because if we're going to use it for pencils, we don't want really heavy pencils. We want quite lightweight ones because we want them to be portable. Okay, graphite's insoluble. Thankfully, if you put a pencil in water, it won't dissolve. And this is, again, because you've got lots of strong covalent bonds, and it's going to require far too much energy to break them. Okay, diamonds. Diamond is slightly different, still made from carbon, but it's bonded, each carbon's bonded 4 times in a tetrahedral shape, as you can see here. So if you look at each carbon atom, it's bonded 4 times. So you've got 1, 2, 3, and you'd have 1 that's going behind, which is 4. Okay, so each one has got 4 there. That's probably a bit easier to see this one here. So you can see you've got 1, 2, 3, 4. Okay, so each one's bonded 4 times. Tightly packed, rigid arrangement. Heat can conduct well in diamonds. Unlike graphite, though, diamonds can be cut to make gemstones, which can be pretty useful. Really high melting points, very high melting points, because we've got lots of strong covalent bonds. It requires loads of energy to overcome them. It's also very hard as well. Diamonds are really hard. They're used on saw tips, and drill bits, etc., because for their durability. It doesn't conduct electricity. It doesn't have any delocalized electrons, so it's a very poor conductor of electricity. And diamond's also insoluble. The covalent bonds are far too strong to break, just like with graphite. And you'll also see silicon dioxide being mentioned as well. It has a similar structure to diamond. So in that case, when you're talking about diamond, silicon dioxide can be talked about in this similar way. Okay, metallic bonding. So metals have a giant metallic lattice structure. Okay, the structure is they have positive metal ions in the middle, and they have a sea of delocalized electrons surrounding them. And them electrons come from the metal atoms that originally were there. And these atoms obviously form ions, and the electrons are now delocalized. We have an electrostatic attraction between the positive metal ions and the delocalized electrons, because they're negatively charged. And this attraction is the metallic bond. Okay, but there's that word again, electrostatic attraction. Okay, and basically the more electrons an atom can donate to the delocalized system, the higher the melting point. So, for example, magnesium has a higher melting point than sodium. Magnesium has can donate 2 electrons to the electron delocalized system, whereas sodium can only donate 1. So therefore, magnesium has a higher melting point because it can donate more electrons into that delocalized system. So they're good thermal conductors. They can the delocalized electrons can transfer this kinetic energy, which is obviously a transfer of heat. This is conduction of heat. They're also good electrical conductors again. The delocalized electrons are mobile. They can move around, and so they can carry that current as well. And the metals have high melting points because they have lots of strong electrostatic attractions. And this is between the delocalized electrons and the positive metal ions. The solid metals are insoluble as well. The metallic bond, just like with covalent bonds, is far too strong to break. So thankfully you can put metals in water and they won't dissolve. And the metals are malleable and ductile, okay, because the ion layers can slide over them when we hit them with a hammer, and they can still retain that attractive force between the delocalized sea of electrons and your positive metal ions. Malleable members is how is basically where we can, if we hit it with a hammer, it can be bent into shape. Ductile means it can be drawn into wires. Either way, if we reform these metals, then the structure still remains the same because of that attraction remaining intact. Okay, shapes of molecules. Now this is really important for covalent bonding in particular. So we can use the number of bond pairs and lone pairs of electrons to work out the shape of a molecule. So molecules have a very specific shape with specific angles. And the reason is because the bonds repel each other equally. So the bonds contain electrons, so they'll want to be as far away from each other as possible. And you can see, here's an example here. So you can see that we've got a lone pair next to a bond pair, and you'll see some examples pop up here in a minute. But you've got a lone pair next to a bond pair. These repel more than 2 bond pairs together. So obviously these are 2 bond pairs together. But if one of them is a lone pair, basically we're going to get greater repulsion between a lone pair and a bond pair. And obviously if we have 2 lone pairs together, these will repel even further. So there's one with 1 lone pair, and there's one with 2. And you can see the bond angle has actually been reduced by quite a bit, because we've got this extra repulsion between the lone pair and the bond pair. So they do change the shape, which is the lone pairs. They do change the shape of these molecules, and generally, for every lone pair that you have, you reduce the remaining bond angles by 2.5 degrees. There is an exception though. You'll find I'll show you the exception as well where this doesn't work. But you can see here, this one, for example, we started at 109.5, reduce it by 2.5 degrees because we've got one lone pair. That gets us to 107, and reduce it again by another 2.5 because we've got two lone pairs, and that reduces it to 104.5. Okay, so you'll see some of the exceptions later on. Okay, so this is how we do it. These are a methodology of working it out. So we're going to, basically the first thing we're going to do is draw our dot cross. And we're going to work out how many bond pairs and lone pairs we have. Okay, so there's a dot cross for methane molecule, for example. Now, if you have ions, all we do is you add electrons to the central atom for negative ions, and we remove them for positive ions. So, for example, NH4+, now nitrogen normally has 5 electrons in its outer shell. If we've got that plus charge, then we would say we'd take an electron away from the central atom, which would be the nitrogen, and so that means it will have 4 electrons left. Now, these are all involved in bonding, and so the shape would be tetrahedral, but we'll have a look at the shapes a little bit later on. But this is just a method of working out bond angle. Obviously, in reality, that doesn't happen. We're not removing electrons from the middle atom. This is just a method for working out your shape. Okay, so basically the total tells you the shape of the molecule. So this one's tetrahedral, but I'll show you that later. So if you have lone pairs, you need to replace the bond pairs for lone pairs. Then you change the shape and the bond angle, which we'll look at in a minute. So you can see here, obviously, this one has got 4 bond pairs. There's no lone pairs on the central carbon atom here. So bond pairs 4, lone pairs none. The total is 4. And it's this number that's going to tell us, obviously, what the shape is going to be. So looking at one with lone pairs then, this is water. You can see this has obviously got 2 bond pairs and 2 lone pairs. There it is there. 2 bond pairs, 2 lone pairs. The total's 4 though. And this is basically telling us that it's based on a tetrahedral, so that's our starting molecule, but it has 2 lone pairs, and so what we do is reduce the angle by 2 lots of 2.5, which is 5 degrees. So what we're going to do is we're now going to look at some of these shapes. We're going to look at the ones with no lone pairs first, because this is what are going to be our base molecules, and then we're going to look at the ones with lone pairs, which make them a little bit trickier. Okay, so shapes of molecules with no lone pairs. So again, remember using that rule, number of bond pairs and number of lone pairs. If you've got a situation where we've got 2 bond pairs and no lone pairs, an example could be BeCl2, then we get a linear shape and the angle is 180 degrees between the 2 bond pairs. So they want to be as far away from each other as possible, remember. Okay, if we've got a situation where we have 3 bond pairs and no lone pairs, we form a trigonal planar shape. And you can see an example would be BF3. And this is trigonal planar, this one here. The bond angle is 120 degrees. If we get a situation where we've got 4 bond pairs and no lone pairs, just like what we've seen before, an example would be methane, CH4, then we form tetrahedral shape. This is called tetrahedral. And you can see it here, the bond angle is 109.5, but notice this is now 3D. So we have these ones are in your plane of vision, these 2 here. This wedge means it's coming towards you, and this dotted line means it's going away from you. So it's like a 3-dimensional shape. The bond angle between this is 109.5. Okay, if we come across a one where we've got 5 bond pairs and no lone pairs, for example, PCl5, the name of the shape is called trigonal bipyramidal. And you see this is it just forming here. Now this is unusual in the fact that it has 2 bond angles. See there? You see here we've got this trigonal bit in the middle, which is this 3 bit here. That's the flat bit. Basically, it's just that molecule tipped on its side. So that's 120 degrees. Then we have these 2 axes here, top and bottom. So that's going to be 90 degrees between this axis and the trigonal planar bit here. Now we'll call it bipyramidal because if I draw a line from here to here, and then here to here, and then there to there, then we form this pyramid shape on the top. And we do the same on the bottom, we'll form a pyramid on the bottom as well. That's what we call it bipyramidal. So it's trigonal bipyramidal. And if we get a 6 bond pairs and no lone pairs, then what we form is an octahedral shape. An example of that would be SF6. Now it's octahedral because even though it contains 6 bonds, if we were to draw this as a 3D shape, it would form an octahedral shape. So if I was to draw a line from there to there, there to there, there to there, and there to there, it would have a 4-sided shape on the top, and would have a 4-sided shape on the bottom as well. And so obviously 4 plus 4 is 8, so it's an 8-sided shape. But the number of obviously bonds is 6. So the bond angle here is just 90. We've got the square shape in the middle, and then the two axes top and bottom. Okay, let's have a look at the ones with lone pairs then. Okay, so if we've got 3 bond pairs and 1 lone pair, an example with ammonia, the name of the shape is pyramidal. Now this is based on a tetrahedral, so except we have a lone pair. So remember the tetrahedral bond angle was 109.5. For every lone pair we take away 2.5 degrees, so we're left with 107 degrees on the bottom here. So this is a pyramidal shape, which is this one here. So an example would be ammonia. 2 bond pairs and 2 lone pairs is going to be something like this here. Okay, so which is water. The name of the shape is bent, and you can see here that this would have been based on a tetrahedral because we've got 1, 2, 3, 4 pairs of electrons. 2 of them are lone pairs though, so we reduced the bond angle by 2 lots of 2.5, which is 5 degrees. Was based on 109.5 minus the 5 gives us 104.5. Okay, and that's how we work that out. 3 bond pairs and 2 lone pairs. Now this forms a trigonal planar shape. There it is there. This would have been based on a trigonal bipyramidal shape. But you can see here that we've taken the 2 bonds away. We've now got 2 lone pairs. Now this is where the bond angle remains the same compared to the trigonal planar. This repels equally against that one. So these lone pairs will push these ones upwards, but these ones will push them downwards. Because they repel equally, we get no change in bond angle. So that's one of the exceptions. And the final one is 4 bond pairs, 2 lone pairs. An example is XCF4. Square planar is that one. 90 degrees between each of them. Very similar to this. We've just taken the 2 axes away and they repel equally. So that's the key thing. There you go. Bond angle remains unchanged. 2 lone pairs, they'll repel equally from each side, from opposite sides. Okay, so the bond angle remains 90 degrees. Okay, so let's summarise some of this bonding then, because we've seen quite a few bonding, or quite a few different types of bonds here. Just giant covalent, example, graphite diamond silicon dioxide, solid at room temperature. They do conduct, they don't conduct electricity as a solid, and they don't conduct electricity as a liquid either. And the only one which will conduct as a solid is graphite. That's the only one that you need to know that conducts electricity. Doesn't dissolve in water, really high melting points because we got high, strong covalent bonds. So lots of them, so it's going to be a really high melting point and boiling point. Simple molecular, these are the shorter molecules, things like iodine, ammonia, water, the shorter molecules. Usual state, room temperature and pressure, they're normally liquids or gases. They don't conduct electricity when they're solid or liquid. They might be soluble in water, it depends on the polarity, we'll have a look at that in a minute. The melting points and boiling points are low. Remember, we're breaking weak forces here, not the bonds. Okay, so that's why they've got low boiling and melting points. Giant ionic are things like sodium chloride, calcium oxide, etc. Usual state is solid. They don't conduct electricity when they're a solid, but they will conduct electricity if they're a liquid because we have these free moving ions. And they will do it actually when they're dissolved in water for that reason. They are soluble in water because they're charged, so they're ionic, and their melting and boiling points are really high. They have lots of strong electrostatic forces attracting these oppositely charged ions, so they're going to have high melting and boiling points. And metallic bonding, these are obviously just metals. Usual state is obviously solid. Yes, they do conduct electricity when they're solid because they have this delocalized electrons. They do when they're a liquid because they still have them delocalized electrons. They don't dissolve in water. The bonds are far too strong to break. And their melting points are high because we need loads of energy to break these electrostatic forces between the positive metal ions and the delocalized electrons. Now, this polar bit is obviously quite important. So polar molecules, they dissolve well in polar solvents like water. So look out for polarity in your molecules. And non-polar molecules, for example, hydrocarbons, they don't dissolve in water. They don't dissolve very well whatsoever. So you need to use a non-polar solvent for that. So that's why we're saying it depends on the polarity of the molecule. Okay, and that's it. That is bonding and structure. please subscribe to the channel. Show your support for the channel. That'll be really great. You know, all the videos are free. They're all there to use. Just get yourself subscribed. Doesn't cost you anything. Just click on the circle in the middle, and you'll be able to get your all the up-to-date information on the videos that we upload. And also, please feel free to get a hold of these PowerPoints. You can purchase them just clicking in the link in the description box, and you can get a hold of them there. But that's it. Bye bye.